Welcome to our video lecture on topic 5.1, measuring energy changes. If you don't already have a data booklet and calculator nearby, pause the video, go grab them. You're going to want them today. Our objectives are these. We're going to define, so many vocabulary words. We're going to describe the law of conservation of energy, which is also the first law of thermodynamics. We're going to use this a lot in our unit. We're going to explain some endothermic and exothermic processes. We're going to identify endothermic and exothermic processes and reactions using potential energy diagrams. We're going to define this amazing thing called activation energy. Then we're going to annotate some of those potential energy diagrams to show the effects of catalysts on that activation energy. We're going to use Q equals mc delta T. This is an amazing formula. Memorize it. We're going to use that to calculate some energy changes in both processes and reactions, and we're going to calculate energy changes from enthalpies of formation and enthalpies of combustion, and that is why you want your data booklet. Our essential understanding for today, the enthalpy changes, and we're going to talk a lot about what enthalpy is. These changes that happen in chemical reactions can be calculated from their effect on the temperature of their surroundings. So it's really hard for us to know exactly what kind of energy changes are happening in a reaction by just looking at the reaction. So instead we look at how energy is released or absorbed, and we can find that by looking at the temperature of the surroundings of the reaction. So this word enthalpy. Enthalpy is the internal or the potential energy, the chemical energy that's stored in the reactants, and then also later stored in the products. We can only measure the changes in the enthalpy. We can't actually stick a probe into a chemical and be like, it has this much potential energy. We can only figure out how much energy was stored if we release it. So it's kind of a quirky deal. Heat, however, is that transfer of enthalpy due to temperature differences. So most of the time we're going to be looking at heat, that change in enthalpy. Heat is the change in enthalpy. Temperature is a little bit different from heat. So temperature is actually a measure of the average kinetic energy of particles in a system. If you have ever watched Karate Kid, you know how Mr. Miyagi claps his hands and the friction of his hands makes his hands nice and warm, and then he cures everything because of that temperature. This is all about kinetic energy. The faster things are moving, the warmer they are. We're also going to talk about thermodynamics, which in IB world, we call energetics, thermodynamics, same thing. It's the study of energy in chemistry and how we convert it in some chemical reactions and chemical processes. The first law of thermodynamics is the conservation of energy, and we are going to apply this so much in our lab work. So this law of conservation of energy, energy is conserved. It can neither be created nor destroyed, but we can transfer it and transform it. And we're going to talk a lot about how we transform potential energy into kinetic energy. That potential energy for us is going to be lots of chemical energy. In physics, potential energy is often the position of a thing, right? So if you have a ball and you hold the ball up high, it has lots of potential energy. That potential energy is transformed into kinetic energy as it falls. For us, it's going to be more about the potential energy that is stored in chemical bonds, the position of those bonds, and then temperature is going to be our measure of kinetic energy here in chemistry. Lots of different ways that we can transform energy. We can go from chemical energy, the ice cream that we eat. We take that glucose, turn it into ATP, use that ATP to move our muscles. So we can transform energy from chemical into motion. We can take sunshine, radiant energy. Plants can turn it into chemicals, glucose and photosynthesis. Lots of different ways that we can transform energy. So this cool thing called heat. So heat, we denote with the letter Q. Lowercase q is heat. I know there's no Q in heat, but that's what we use. So Q is the same thing as heat. And what's kind of cool about heat is it's not the same as temperature. Not the same as temperature in chemistry. So instead, heat is about the energy that is transferred from a warmer body to a cooler body. So if I put on my hand, let's pretend like that's a hand. If I put a piece of ice on my hand, then my hand is going to transfer energy from my body into the piece of ice, and that's what's going to make the ice melt. So the ice will get warmer because my hand is getting colder because we're transferring energy from a warmer body, my hand, to the cooler body, the ice. This is heat. It's thermal energy, but it's not the same as temperature. Temperature is all about motion, movement, the kinetic energy of molecules, particles in a system. Absolute zero means that there is no kinetic energy. There's no more movement. You might be thinking, but solids, they must be all at absolute zero because they don't move. That is not true. As you can see in this lovely video thing happening here, the kinetic energy of even solid particles, they're always wiggling and jiggling just a little bit. Until we get to absolute zero, which is 0 Kelvin or negative 273 degrees Celsius. And at that point, all motion will stop. We're not really sure what will happen. Physicists think they know what will happen, but it's kind of crazy to imagine, like everything just, no more movement, no electrons, nothing is moving, everything stops. Crazy sauce. We're also going to briefly talk about this thing called entropy. Entropy is not a big part of SL Chem. We would talk about it more in HL. But entropy at absolute zero would also have its minimum possible value. Entropy is kind of like disorder or chaos. That's a very simplified view of entropy, but it's really about the distribution of energy among particles in a system. The more spread out things are, the more stable they are, and that's what entropy is all about, is that stability, because energy is well distributed. So systems and surroundings, quick little definitions, and these I think are all very self-explanatory, but we're going to talk about them just in case. So the system that we'll be talking about will be our reactants and products, and if we have things dissolved in water, then the solvent will be part of the system. The surroundings are where the reaction is taking place. In an open system, we're going to have a transfer of matter and energy from the system into the surroundings both ways. So if I had a beaker and I had some acid and I tossed in a piece of magnesium, we're going to have some hydrogen gas propagate and leave the beaker. This would be an open system. If I took that same beaker and I covered it with a balloon and had some acid and that piece of magnesium, then that gas will still be propagated, but it's going to be trapped in the balloon. It'll be a closed system. I can still feel the bottom of the beaker, and I will feel heat because this will be hotter than my hand. And so we'll still have heat able to move out of the system or into the system. An isolated system is what we're going to try to get so that we can keep the heat inside and measure just what's happening inside the system, less so in the surroundings. Neither matter nor energy can be transferred across the boundaries. We don't have great tools to make this happen, but we're going to pretend a little bit. So chemical energy in bonds. Chemical energy is stored in bonds. What's interesting about our chemical bonds is if I want to break them, I have to add some energy. So that's endothermic energy is going in. So endothermic energy adding into the system. Energy input is required for bonds, chemical bonds to break. We call this bond dissociation energy. This is the energy required to break any particular bond. Bond enthalpy is the average energy required to break a mole of the bonds of a gaseous covalent molecule under standard conditions. Lots of extra words in there, but what's kind of cool is we actually do have that data in table 11 of our data booklet. So in a couple more lectures, we're going to look at bond enthalpies, and we're going to talk about the energy required to break bonds. Making chemical bonds is actually exothermic because the formation of a bond is slightly more stable than these guys being free radicals all over the place. And so this making of bonds as exothermic energy is released. We can use table 11 for that too. We're just going to switch the signs. Endothermic, because we're adding energy, is positive. Exothermic energy is being released. It's going to be negative energy change, positive energy change for endothermic. So this idea of changes in enthalpy or heats of reaction, sometimes we also call it the enthalpy of reaction. So all of these we can refer, they're kind of all the same thing. We refer to them with delta H. So delta H, or change in enthalpy, because H is our letter for enthalpy. There actually is an H in enthalpy. That's exciting. So delta H is our change in enthalpy, interestingly, because it's also the heat of the reaction, that transfer of thermal energy from a warmer body to a cooler body. Delta H is the same thing as Q. Q and delta H are the same thing. Q and delta H are pretty much the same thing. We can use them interchangeably. Heat of reaction, change in enthalpy, enthalpy of reaction, these are all the same things. Most of the time we're going to measure them in kilojoules. Or if I'm looking at molar enthalpy, then it's going to be kilojoules per mole. I know I've got a lot of scribbles here. we can have that in kilojoules per mole, mole to the -1. That would make it molar enthalpy. Kilojoules by itself would just be the enthalpy without the moles. We can have endothermic or exothermic reactions. Endothermic reactions are going to add heat. We're adding more, increasing the amount of enthalpy stored in the species of the reaction, and it's going to be a positive delta H. We're adding energy. We need more energy to break the bonds than we release when we form the new bonds. And then exothermic is going to be a negative delta H. We're releasing that energy. More energy is released during bond formation than we need to break the bonds during that initial stage of popping all those reactants apart. So endothermic is going to look like this. We have lots of heat energy in. So much energy needs to be added to go from the reactants to all kind of broken apart like this. But then only a little heat is released when we go back to some new bonds being formed. Only a little bit of heat is released. And so this would be an endothermic reaction. Notice that the reactants have less energy. The products have more energy. We have added some of that enthalpy to get from the reactants to the products. The opposite happens when we have an exothermic reaction. So here just a little bit of energy is needed to break apart all the bonds. So here my reactants, a little bit of energy is needed to break all those bonds. And then so much energy is released when we go and make the new bonds. So much energy is released when we form our new bonds. Notice that the energy of the products is lower than the energy of the reactants because we have delta H going from here down to here. It's a negative delta H. That enthalpy, that energy was released. It's exothermic. Good? All right. So this idea of activation energy, or E to the sub A, we can show in a potential energy diagram like we were looking at the exothermic and endothermic reactions on the previous slide. So here's my starting energy, the energy of my reactants, the energy required to break all those bonds, that minimum amount of energy required for the reaction to occur, and it's occurring because we're breaking the bonds of the reactants, is known as the activation energy. And then, of course, we're going to release energy as new bonds are formed. Ending energy is here, which means that this is a negative delta H. This one happens to be an exothermic reaction. But the difference between the starting energy and that energy required to break the bonds of the reactants is known as the activation energy, the minimum amount of energy required for a reaction to occur. That's a good vocab word to remember. So what's kind of cool about that activation energy is we can actually reduce it by using this super cool thing called catalyst. So catalysts are species that are not consumed during a reaction, but they will reduce the activation energy and therefore speed up the rate of the chemical reaction. In biology, a lot of times our catalysts are enzymes. So if you're thinking, I think I've heard this word before, you have catalysts in bio are enzymes. So reaction with a catalyst, reaction without a catalyst, my potential energy diagram. So these are my reactants. This is the energy stored in the reactants. The activation energy without a catalyst is so tall, all the way up to here. So this amount of energy is required to break all the bonds of the reactants to get the reaction to happen. If I add a catalyst, notice that my activation energy is reduced. I need only this much activation energy, this much energy to break all those bonds in the reactants to get the reaction to proceed. So those catalysts reduce the activation energy. We can show that on a potential energy diagram. Sometimes we call these enthalpy diagrams. Notice that the activation energy without the catalyst is way up here. With the catalyst is lesser, it's right here. Let's talk about the rest of our reaction. So we know that energy is released when those new bonds are formed. The total energy stored in the products is the same at the end of the reaction. So the catalyst does not change how much energy is in the products, it only changes this activation energy in the middle. Since my reactants are here and my product's energy is up here, this is a positive delta H. This happens to be an endothermic reaction. And that endothermic reaction has a slightly smaller activation energy because we added that catalyst. You might be wondering just how does this catalyst reduce activation energy? Well, what happens is the catalyst will bind to the reactants, this initial state. The catalyst will then put some strains on the bonds, the chemical bonds in the reactants, make it a little bit easier to break those chemical bonds. Less energy is required because the catalyst is putting the strain on those bonds. It just makes it a little bit easier. We usually will have many steps involved. It's usually not just a one and go. So the catalyst will put some strains on the bonds. We'll still need that activation energy to break those bonds. We just don't need as much because of the strain coming from the catalyst. And then we end up with products. The catalyst will release the products. The catalyst can then be used again. The catalyst is not consumed during the reaction, which makes it super convenient in industry. We can use catalysts a lot. And again, the goal is to reduce activation energy. Notice that with the catalyst, we go from energy of reactants here, and then our activation energy is pretty small compared to activation energy without the catalyst is so giant. And then, of course, we're going to end up with the same amount of energy in the products at the very end of the reaction. And because reactants are here and products are lower, we do have a negative delta H. This happens to be an exothermic reaction. Enough words about enthalpy changes. Let's go ahead and calculate some enthalpy changes. Remember that that is the same thing as calculating heat of reaction because they are the same things. Our equation is this, mc delta T, and that's going to be equal to heat, which is Q. It's also equal to delta H because we know that the change in enthalpy, delta H, is the same thing as Q, the heat of reaction. They're all the same things. Change in enthalpy and Q are the same things. MC delta T is our formula. We don't need to memorize that because it's given to us in our data booklet, table 1. What is M? M is mass. What is C? C is specific heat. What is delta T? Delta T is the change in temperature. And we're going to calculate that by T final minus T initial. Final temperature minus initial temperature is going to give us the change in temperature, delta T. Let's talk about this super cool thing, C, specific heat. Specific heat is the amount of energy required to change a specific quantity mass of a substance by a specific temperature change. Most of the time we're going to talk about kilograms and Kelvin here in IB Chem. So for water, the specific heat, this is a constant. We refer to it as C, which is weird. I mean, there is a C in specific heat, but okay. So C is specific heat, 4.18 kilojoules per kilogram per Kelvin. 4.18 kilojoules of energy is needed to heat 1 kilogram of water by 1 Kelvin. This constant is given to us in data booklet, table number 2. Let's apply some Q equals MC delta T to these two problems. How much heat is needed to heat 10 kilograms of water from 10 degrees Celsius to 20 degrees Celsius? So M is here. Here's my mass. Specific heat is here. It's a constant, 4.18 kilojoules per kilogram Kelvin. My temperature change is going to be here. Here's T initial. Here is, T final temperature. So we're going to subtract them. You might be thinking, but look, we need to change to Kelvin. We can, but we don't actually have to. And I will show you why. We know that to get from Celsius to Kelvin, we're going to add 273. So 10 plus 273 is 283. To get from 20 to Kelvin, we're going to add 273, and we're going to get to 293. Here's my T final. Here's my T initial. 293 minus 283 is 10 Kelvin. 20 minus 10 is also 10. So my delta T, it doesn't matter if I'm in Kelvin or Celsius because the increments are equal to each other. So even though the numbers are different, because the increments are the same, the change in temperature will be the same. So you don't have to convert to Kelvin. You can, but you don't have to. So delta T is going to be 10. Q equals MC delta T. Here's my M, 10 kilograms. Specific heat, 4.18 kilojoules per kilogram per Kelvin. Remember that my negative exponents mean divided by, right? So my per's in the denominator. And then my delta T was 10 Kelvin. 10 times 4.18 times 10. 10 times 10 is 100. 100 means that I multiply, I move my decimal place 2 times to the right. So my final answer is going to be 418. unit labels. Kilograms and per kilogram cancel out. Per Kelvin and Kelvin also cancel out. And so all that I'm left with is kilojoules, which is good because kilojoules is my unit of energy. And I'm looking for that heat energy needed to heat up that water. 418 kilojoules of energy is needed to heat up those 10 kilograms of water from 10 degrees Celsius up to 20 degrees Celsius. Good? All right, let's look at this next one. How much heat is released when 20 grams of water cools from 100 Celsius down to 50 Celsius? So you might be going, oh, we've got to convert again because I've got grams and my specific heat is given in kilograms. Here's a crazy cool thing about specific heat. So 4.18 kilojoules per kilogram Kelvin or Celsius. I'm going to get rid of my kilojoules and turn my kilojoules into joules. I've got kilojoules on the top. I'm going to put kilojoules on the bottom. Turn my kilojoules into joules. I know that there's 1,000 joules and 1 kilojoule. So here I have canceled out kilojoules. Now I'm going to get rid of my kilograms. I've got kilograms on the bottom. I'm going to put kilograms on the top, turn my kilograms into grams. I know that there's 1,000 grams and 1 kilogram. So here I have successfully canceled out kilograms, top and bottom. But you know what else I can cancel out? 1,000 on the top and the bottom, which means that what I'm left with here is 4.18 joules per gram Kelvin. And so my number here stays the same as it stayed here, but I can get rid of both of the kilos and go down to joules per gram because of that conversion. Let's go ahead and do this problem now. Q equals mc delta T. Here's my M. My specific heat is 4.18 joules per gram Kelvin. My delta T is going to be careful here, T final is 50, T initial, temperature initial is 100. So my delta T is negative 50 degrees Celsius. My temperature went down, that water cooled off. So when I do Q equals mc delta T, we're going to get those 20 grams of water times 4.18 joules per gram Kelvin or Celsius, same thing, times negative 50 Celsius. 20 times 50 is 1,000. 1,000 times 4.18 is 4,180. And my unit label is going to be, because grams cancels out, and Celsius and Kelvin, because delta T's are the same, cancels out. We're left with just joules. 4,180 joules is released, which means that that negative right there tells us that that energy is being released and not absorbed. If you don't love joules, you can go ahead and convert back to kilojoules by dividing by 1,000. Negative 4.18 kilojoules is that change in enthalpy. 4,180 joules of energy is released when that water cools off. Good? Let's do another one where we actually have a chemical reaction happening now. So we can use these super cool things called calorimeters because we're measuring calories, another unit like joules. So we can use these calorimeters to measure these energy changes, enthalpy changes in reactions and other processes. We're still going to use Q equals mc delta T. I'm still going to use my specific heat of water because I have this crazy dilute hydrochloric acid, which means that most of it is water. So I'm going to use specific heat of water. So this calorimeter, and it's literally 2 coffee cups stuck inside each other so that we have extra insulation power, filled with that watery hydrochloric acid. We're going to dump our baking soda, sodium hydrogen carbonate, into it. We're starting at 20 degrees Celsius. So my thermometer here is letting me know that I've got 20 degrees Celsius to start. We toss in that sodium hydrogen carbonate, and the temperature goes up to 31 degrees Celsius. So I watched my thermometer went up, up, up. I have this stir in here because I don't want like a little hot pocket of stuff here and a cold pocket of stuff here. that stir helps to keep that distribution of temperature changes equal so that I have a fair temperature change coming from my thermometer. So let's calculate that heat energy. We're going to use Q equals mc delta T. M is going to be, here's where it gets interesting. I'm going to use the mass of my hydrochloric acid because that's really the temperature change. That's the temperature, that's the stuff where the temperature is changing. So I'm going to use my mass of dilute hydrochloric acid. My specific heat, because it's mostly water, I'm going to go ahead and use 4.18 joules per gram degree Celsius or Kelvin. And then my temperature change, here's T final, here's T initial, 31 minus 20 is going to give me 11 degrees Celsius is my change in temperature. Good. So now with my handy dandy calculator, I'm going to do 50 times 4.18 times 11, and we get 2299 joules of energy is released. I could also say that that energy was released by the reaction, but absorbed by the hydrochloric acid solution. So kind of a weird thing, and this is where we go back to that law of conservation of energy. So this energy that was gained by the acid solution was actually released by the reaction. So it's both endothermic and exothermic at the same time. If I wanted to, I could convert that to kilojoules, divide by 1,123, 2.299 kilojoules of energy is gained by the solution, released by the reaction. What if I took that same question, we just decided it was 2.299 kilojoules was gained by the solution, released by the reaction. Now I want to find out what is the molar energy or enthalpy in kilojoules per mole. So here's where things get crazier, right? Because I definitely in the last problem used the mass of the solutions because that's what temperature was changing. But now I'm going to use the moles of baking soda that I threw into the calorimeter to find molar enthalpy. So we're going to take those 2 grams of sodium hydrogen carbonate, baking soda. Whoa, I lost an A there, sodium hydrogen carbonate. I'm going to convert my grams into moles. I'm going to find 22.99 plus 1.01 plus 12.01 plus 3 times 16 gives us a grand total of 84.01 grams per mole. 84.01 grams per mole. My grams top and bottom cancel out. We're left with moles. 2 divided by 84.01 gives us 0.024 moles of sodium hydrogen carbonate baking soda. So I want to find kilojoule per mole. Again, remember that that -1 exponent means that it's in the denominator. I'm dividing by. So I'm going to take my kilojoules, 2.299, and divide it by 0.024 moles, kilojoules divided by moles, and that's going to give us 95.791, lots of digits. So we get to keep 2 sig figs. That 7 is going to turn that 5 into a 6. Our final answer is going to be 96 kilojoules per mole. And depending on if you want to argue the energy absorbed by the solution, 96 kilojoules of energy given to the solution, but because this mole number is really about our baking soda and that energy was released in the reaction, better to say negative 96 kilojoules per mole. 96 kilojoules of energy was released by this reaction per mole of the reaction, and that's what heated up that dilute hydrochloric acid solution. Good? All right, let's do some more. So here I have a table of specific heats, and let's say that I am going to add 10 joules of energy to 10 grams of each of these metals, and they start at the same initial temperature. I want to figure out which one's going to get the warmest. So if we start them all at the same temperature, and I have 10 grams of each of them, and I add the same amount of energy, thinking about that specific heat and what specific heat means, which one's going to get the warmest? Copper requires 0.385 joules of energy to warm up 1 gram by 1 Kelvin. Silver needs 0.234, gold needs 0.130, platinum needs 0.134. Because gold needs the least amount of energy to warm up by 1 degree Celsius or 1 Kelvin, it's going to get the warmest the fastest. So gold will actually end up being the warmest of the metals because so little energy is needed to change its temperature. And I want you to take a quick look at this specific heat, 0.130 joules per gram Kelvin. For water, it's 4.18. That's, 40 times more energy is needed to heat up water than to heat up gold. This is why water is such an amazing buffer for temperature changes in especially biological systems. We're going to put away Q equals mc delta T for a little bit and look at another way to calculate enthalpy changes. So we have enthalpy changes of formation. So lots of scientists have done lots of amazing work to figure out the energy changes needed to form 1 mole of substances, and those energy changes are given to us in their data booklet in table 12. We refer to this energy change of formation with delta H, energy or enthalpy change of formation. And because different amounts of energy are required for different pressures and temperatures and whatnot, we say that they're in standard state, which is what that guy is going to be. So standard state formation delta H is what's given to us in table 12. And then I can use these energy changes of formation to calculate the reaction by taking the total sum of all of the energies in the products and then subtracting the sum of all the energies in the reactants. This makes a lot of sense if we think about it in a potential energy diagram. So here I can see that my reactants have 50 kilojoules of energy and my products have 100. I know that I need to get from reactant to product, and to do that I'm going to have to add 50 kilojoules of energy to get from 50 up to 100. If I use these numbers in this equation, then products are 100 minus reactants are 50. Again, I'm going to get that positive 50 kilojoules is my delta H of reaction, my heat of reaction. We have a positive or endothermic 50 kilojoules of energy required to get from reactants to products. Good. So this is what it looks like in a potential energy diagram. Let's see what it looks like with table 12 of our data booklet. Again, table 12 here is going to give us those heats of formation for different species that we use a lot. So we're going to focus here on delta H of formation. Delta G gives free energy, and then entropy. We would use those in HL Chem. We're not using those in SL Chem, so just ignore those 2 columns for now. Delta H formation is what we're going to be focusing on. So I'm going to find my products first. So I want to find the sum of 3 CO2s and 4 H2Os. I'm going to subtract the sum of all of my reactants, my propane, and then those 5 oxygens. Good. So I'm going to take 3 times CO2. I'm going to find CO2. CO2 is here, carbon dioxide, negative 393.5. I've got 3 of them. So I'm going to do 3 times negative 393.5. I'm going to add to that 4 waters. Let's see, where's water? Ooh, I've got 2 waters, my friends. So make sure that you're checking your state of matter symbols. Liquid, I want this one, not this one. Negative 285.8 plus 4 times negative 285.8. And this is the sum of the enthalpies of my products minus reactants. minus, and I'm going to add up all of my reactants. C3H8, C3H8 is here. Propane is a negative 105. Negative 105 plus 5 times oxygen. Oxygen is not on my table. Oh no, whatever shall we do? Here's the quirky thing. Stuff that just occurs naturally, oxygen as an element occurs as O2. No energy is needed to form it because it just forms. It just is. And so the enthalpy of formation of naturally occurring elemental oxygen is a 0. No energy needed. It just happens. So now calculator time. We've got a 3 times negative 393.5 plus 4 times negative 285.8 minus negative 105 plus 0 is going to give us a delta H of negative 2218.7. With my sig figs, because this one is in a ones place, we're going to keep a ones place. That 7 is going to turn that 8 into a 9. And my final answer will be negative 2219 kilojoules. Whoa. Per mole of propane is going to be our delta H of reaction. Good? All right. So now we're going to look at not table 12, but table 13. Table 13 is going to give us the enthalpies of combustion. Our previous slide, we literally found this exact thing, right? We decided it was negative 2219 kilojoules. Are you ready for this? We could have just looked at table 13 and found propane, and oh, there's our answer right there. So we did all that work and we didn't have to, but now we know how to. So that's good. But be aware, if you're given a question with combustion, you can go straight to table 13. If you're given a question about heats of formation that's not combustion, then you do actually have to use table 12. Good? All right, one more problem and then we are calling this lecture done, my friends. All right, so enthalpy of reaction. Sometimes we are going to use balanced chemical equations and some stoichiometry, which is going to include our delta H's, and that'll help us figure out enthalpy changes given specific amounts of stuff in our reactions. So if this question is asking me what amount of energy will be released if 4 moles of nitrogen gas reacts when ammonia is formed, then I can use, just like I would in regular old stoichiometry, I can use this number kind of like a mole ratio. So I've got 4 moles of nitrogen gas. This is my given, and I want to convert my given into energy, which means that I need to get rid of N2. I'm going to put N2 on the bottom, and I want to convert my N2 into kilojoules, that energy. I'm going to use the coefficient for my balanced equation. It's an invisible 1. I'm going to put a 1 on the bottom. I'm going to put my delta H on the top, make sure that we keep our sign. So that negative 92.2 is going to go on the top. So my N2 cancels out top and bottom, and then I can just multiply 4 by negative 92.2. 4 times negative 92.2 is going to give me a negative 368.8. We're going to go ahead and check our sig figs. We get to keep 2, so that 8 is going to turn that 6 into a 7, negative 370 kilojoules will be the enthalpy change if I have 4 moles of nitrogen gas reacting. This makes a lot of sense because if I have 1 mole of nitrogen gas, I get 92. If I have 4 moles, I should get 4 times that. I should get negative 370 kilojoules of energy is that enthalpy change. Good? One more and we're done. What amount of energy will be released when 25 grams of ammonia is produced? This one's a little bit trickier because I'm starting with grams, not moles, but we're still going to just do some basic stoichiometry. Ammonia is NH3. I'm going to get rid of grams, turn those grams into moles because these coefficients, remember, are our mole ratios, not our gram ratios. So 25 grams of ammonia nitrogen is 14.01, hydrogen is 1.01. Add those up together and we get a grand total of 17.04 grams per mole for ammonia. Grams top and bottom cancel out. We now have moles of ammonia. As soon as we have moles of ammonia, we can use our delta H just like it's part of the mole ratios. I'm going to put ammonia on the bottom. I'm going to put kilojoules on the top. Check a coefficient for ammonia. There's a 2 there, so I do need to keep that 2 because it's negative 92.2 kilojoules for every 2 moles of ammonia, not 1. So now I can cancel out ammonia top and bottom. Calculator time. 25 times 1 divided by 17.04 times negative 92.2 divided by 2 is going to give us a negative, don't lose that sign, negative 67.634, lots of digits. We get to keep 1, 2, 3 sig figs, 1, 2, 3. That 3 doesn't do anything to that 6. Our final answer is negative 67.6 kilojoules of energy released when all that ammonia is produced. Good? Great, we did it. We talked about so many words, enthalpy and heat. We talked about that first law of thermodynamics, our law of conservation of energy. We explained that endothermic and exothermic processes exist, energy in, energy out. We looked at how we can find endothermic and exothermic on potential energy diagrams. If the reactants and the products, there's less reactants, more products, it's endothermic, that's a positive delta H. If we have products up here, reactants up here and products down here, then we have a negative delta H, that's exothermic. We talked about activation energy, that's that energy required to get that reaction to occur. And then we showed how catalysts can actually lower the activation energy. So catalysts would lower that activation energy. We talked about Q equals MC delta T. We also talked about the sum of the energies of the products minus the sum of the energies of the reactants. We could also use that to find energy changes using heats of formation and heats of combustion. Good work, my friends.